Hello everyone, welcome to Mind is Pen Education. Last video we have seen in case of single variable, if we have this function and if we want to approximate this function near some point x, then we can approximate this function using the tangent, right? And we have seen that the relation between change in input and the overall, due to this change, the overall change in the function have the linear relation, right? If this change is very small, right? So this change in function and due to this change in input have the linear relation, and how much change is going to happen on the function, that will be told by this linear operator, right? So this linear operator is acting on this change in input and it is telling you that how much the overall function will change, right? And this linear operator is nothing but just the derivative. So you can think of this derivative that tells you that if you change the input, how much this output will get changed, right? And obviously we have already talked about that this change should be very little, infinitely small, right? So now in this video we are going to talk about further, and we will have the function that will take the vector as an input and it produces a scalar quantity as output, and we have already seen these kind of function, the examples of these kind of function, right? So for this kind of function, what happens to the output, or what happens to the change in overall function if we change the input? So here the input is a vector, so this x is a vector and it will have some m component. So x belongs to some m dimensional vector, right? So this is a vector. So if you change this x, so little bit change, or so how do you do that? So let's suppose if you have this vector x, so change in x, change in this vector x means you are changing little bit, this maybe like this. So this is change in, so this is the change in this vector, that is dx, right? So what happens to this overall function if you change a little bit this x? So what you have done, you have this vector x and you have little change on this x, and you should be keep in mind that this is not a number, this is a vector, right? So the function calculated at this point minus the function calculated at this point, so this will give you the change in the overall function, right? And this is equal to the linear operator. So linear operator is this, the derivative of this function times the change in input, right? So we have already seen that you can think of the overall change in function that is equal to or we have the direct relation. So let me write this here, not the delta but df, right? So we have seen that if we are approximating the function, we can have the linear relation between the change in input and change in output, right? And this relation that is change in output is equals to some linear operators times change in input. Right, now if you see this the output of this, or the output of the function is a scalar, right? That means this product has to produce a scalar quantity, right? And this dx is a vector, right? That means this has to be a रो वेक्टर, अगर आप रो वेक्टर को कॉलम वेक्टर से मल्टीप्लाई करोगे देन यू विल गेट अ नंबर, राइट? सो this has to be a row vector, so this f dash x has to be a row vector, right? So this change in output is equals to, so this row vector has a special name that we call as the gradient of the function. So this gradient of a function will be a row vector, and that will be get dotted with some vector that is dx, right? And this dot product can be written as we have already seen as a multiplication like this, so transpose times dx. So if we have this kind of function where this function is mapping the taking the input as a vector and producing some scalar, in that case the derivative is nothing but the gradient, okay? And if you are familiar with this multivariable calculus, then you must have seen what is gradient. So how we define the gradient? So let's suppose you have this function of this kind of two variable, that is x y, that is equals to x square plus y square. So what you do, you take the partial derivative with respect to one direction by keeping all other variable fixed, right? So you just need to keep the, so you are taking the partial derivative with respect to x, so you just need to keep other variables fixed. So partial derivative of this function with respect to x by keeping other variable fixed, so that will be 2x. And again now you have another variable that is y, you take the partial derivative of this function with respect to y by keeping other variable fixed, that will be 2y, right? And what you do, you put these partial derivative as a vector of the, as a component of the vector, and this is what you call as a gradient of this function. That is, this is how we denote by inverted triangle. So this is what the how you define the gradient, and this gradient is a vector, gradient is a vector, and basically it gives you the direction in the input space where the function is changing maximal. Alright, so if you have the function that takes the vector from the input space and produces a scalar, right? In that case the derivative is nothing, or this linear operator is nothing but just the gradient of the function, right? In case of single variable calculus, we have seen this linear operator, that is the derivative, that is nothing but the slope of the function, right? So this slope or this linear operator acts on this change in input, and it tells you that how much this function will get changed. In case of the multivariable, this gradient will act on the change in input, and this input is nothing but a vector, so change in input, so this gradient will act on the change in input, and it will tell you that how much the overall change in function is there, right? You must already have seen that about this gradient in multivariable calculus, that finding the gradient using component wise, right? You can find the gradient by doing the partial derivative component wise. Now let's try to look at an example, and we will try to find, so we will have this kind of function and we will try to find the derivative or the gradient in this case. So let's suppose we have this example. So this x is any vector that belongs to some m dimensional space. That means x will have the component that is x1 x2 till xm, right? And this A is any square matrix. It has to be square matrix, right? So A is any square matrix. So A has the let's suppose it is m cross m, and this A doesn't depend upon the input. That means A is constant here. So if you change the x, there will be no effect on A, right? So we are interested that if we change the input, that is if we change this vector x a little bit, then how much the change in overall function, right? So the change in overall this function would be function evaluated at this point minus function evaluated at this point, right? And we have already seen it is equal to nothing but the derivative, that is f dash x times change in input. And here this derivative is nothing but the gradient of this function. If you would like to write in terms of the multiplication, then this will be transpose times this dx. And if you would like to write in terms of the dot product, then this would be gradient of the function dotted with this dx vector. So here this is vector and this will have to be a रो वेक्टर. दैट मीन्स अगर आप रो टाइम्स कॉलम करोगे देन आपको स्केलर क्वांटिटी मिलेगा, राइट? सो दिस इज आवर फंक्शन. अगर हम इसमें थोड़ा सा परटर्ब कर रहे हैं, थोड़ा सा इसको dx को हम चेंज कर रहे हैं, सो लेट्स पुट दिस इनटू दिस फंक्शन. तो हियर वी विल हैव x के जगह क्या हो जाएगा, x प्लस dx का होल ट्रांसपोज a x के जगह in place of x it will be x plus dx minus this fx. so this fx is nothing, x transpose ax, right? अब यहाँ पे आपको ध्यान क्या रखना है कि ऑर्डर का, क्योंकि मैट्रिक्स मल्टीप्लिकेशन कर रहे हैं तो आप a टाइम्स इज जनरली a टाइम्स, अगर दो मैट्रिक्स है या दो वेक्टर है तो a टाइम्स b इज़ नॉट इक्वल टू b टाइम्स a. तो ऑर्डर का ध्यान रखना है अगर आप मल्टीप्लाई कर रहे हो, क्योंकि यहाँ पे आप नंबर्स में नहीं हो. ये x जो है वो नंबर नहीं है. दिस इज रो वेक्टर और अ कॉलम वेक्टर और मैट्रिक्स, राइट? सो दिस dx इज अ वेक्टर एंड दिस a इज अ मैट्रिक्स. सो जब आप मल्टीप्लाई कर रहे हो तो ऑर्डर का ध्यान रखना है. दैट इज व्हाट यू ओनली नीड टू केयर अबाउट, राइट? सो यहाँ पे ये हो जाएगा x ट्रांसपोज a x. सो दिस एंड दिस प्लस dx ट्रांसपोज a x. सो दिस इंटू दिस फिर प्लस x ट्रांसपोज a dx. दैट मीन्स this into this and plus dx transpose a dx minus this term that is x transpose ax, right? अब यहाँ पे देखो कैच क्या है, ये जो टर्म है dx टाइम्स dx, राइट? सो अगर हम dx जो है वो टेंड्स टू 0 है, राइट? सो दिस टर्म विल बी अ हायर ऑर्डर टर्म, राइट? एंड ओवरऑल अगर dx टेंड्स टू 0 है, अगर dx काफ़ी ही छोटा है, देन दिस विल बी नेग्लिजिबल इन कंपेरिजन टू these terms. So this is higher order term and we have already discussed, so we can neglect this will be approximately 0, right? And these two terms will get cancelled, that is x transpose ax and this right? So overall we will have dx transpose ax plus x transpose a dx. Okay, now let's look at this term. So this term is a scalar quantity, right? So this A is a matrix, X is a column vector. So A times X, that is matrix times vector, will be a column vector, right? And this dx, that is little change in X vector, is also a vector, right? And the transpose of that will be a row vector. So row vector times this column vector, that is nothing but just a dot product. You can think of a dot product. So that will give you a scalar quantity. So why that is important? This is important because if this dx transpose ax is scalar, then if you take the transpose on both sides, that is x transpose a transpose dx, so द स्केलर का अगर आप ट्रांसपोज लोगे तो यू विल गेट द सेम स्केलर, राइट? अगर कोई नंबर का ट्रांसपोज ले रहे हो तो वो सेम नंबर रह जाएगा. सो ओवरऑल पॉइंट इज दैट वी कैन राइट दिस थिंग as a that this thing will be equal to the transpose of itself, right? So that is equal to x transpose a transpose dx transpose, right, plus x transpose a dx. Now we can write this. So x transpose we can take the common in the left side, and here it will be dx, not the dx transpose, and you can take this dx as a common on the right side, and in between here we will have the a transpose plus a, right? So this is your change in overall function. So due to change in input, how much change in output will be there? That is nothing but this times change in input. So here your linear operator is this quantity, right? So that means the f dash x, that is equals to x transpose a transpose plus a, right? अगर ये अगर a सिमेट्रिक मैट्रिक्स होता, that means a transpose equals to a होता, then ये change in output would be x transpose 2a, right? Because अगर सिमेट्रिक मैट्रिक्स है तो ये दोनों सेम ही होगा, that means that would be 2a dx, right? So what will be the gradient? So the gradient of the function, that is nothing but the transpose of this, and that will be a transpose plus a times x, right? And you must be aware with the gradient in your multivariable calculus that you can find the gradient component wise. If you have the function, right, you can just go and find the partial derivative component wise, and you just need to put the each partial derivative as a component of this column vector, then you will have the gradient of this function, right? So you must have already gone through in your multivariable class that how to find the gradient of a function, right? And this is a way that we have looked, and you will find that this way of doing or finding the gradient or the derivative of this kind of function is much easier than finding the component wise, right? And one more thing I want to say here. So we have taken the basic definition. We have seen the derivative as a linear operator, right? We have taken the basic definition of the derivative, and from there we have found what will be the derivative of this function, right? And if you observe, so this is nothing but the product of the function, right? So how you do the derivative if you have the product of the function? Like if I ask you what will be the derivative of like sin x times sin x, right? In case of a single random variable, single variable, right? So we can follow the similar rule here also, but the idea behind is to show you from the start is that here now we are not dealing with a function that takes the input from the real space only. We are having the function that takes the input from the n-dimensional space, right? So the overall point here that you need to take care is the so you need to take care of the order, right? So here while multiplying, so I have taken care of the order, so x transpose a times x, right? Because now we are not dealing with the number, we are dealing with the vectors and the matrices. So you must have known that a times b, if a and b is matrix, then you cannot write in general that a times b is equals to b times a, right? This is not generally true in case of the matrix or the vector. So you need to be very careful while writing if you are dealing with the matrices and the vectors, right? Otherwise you will see that you just simply apply the product rule to find the derivative of this function by keeping the order in your mind. That is it, right? And I have taken it from the scratch, from very basic, so that you have the realization that what's the importance of the keeping the things in the order if we are having, or we are talking about in terms of the multivariable calculus where the input is matrix and the vector, right? So let's suppose let's take the same function, that is fx is equals to x transpose ax, right? And let's suppose here the matrix A is the constant matrix. It will not change if you change the x, and x is a vector that have the component x1 and x2, that have the two component. And let's suppose that A is a matrix that is 2 1 1 3, right? And if you go the component wise, let's suppose if you are trying to find the gradient, that how you used to do as of now, then what you will do, first of all you will find the function that is x transpose, that means x1 x2 transpose. A is, let's say 2 1 1 3, and your x vector is x1 and x2, right? And you will do the multiplication, and ultimately you will get the 2x1 square plus 2x1 and x2 plus 3x2 square, right? So this is your function. Now what you will do, in order to find the partial derivative, you will take the partial derivative of this function with respect to the variable x1 by keeping other variable fixed. So that would be 4 x1, and the partial derivative with respect to the x2 variable by keeping the other variable fixed, and that would be 4x1 plus 2x2, right? So here this will be 2x1 plus 6x2, right? Now the gradient, you just need to put these partial derivative as a component of this column vector, right? And if you would like to calculate the gradient at the point let's suppose x is equals to 1 2, right? Then this gradient would be at 1 2, this will be 4 times 4 plus 4, that is 8, and this will be 2 plus 12, that is 14, right? So this is how you used to do as of now to find the gradient of a function, right? And what's the benefit of doing this way? So you just need to find the gradient of this function. So that is the gradient of this function, that is, so this is second method, and this is what you used to do so far. And let's suppose if you have the right now we are dealing just with two variables, right? Let's suppose if you have like 10 20 or hundreds of variable, then doing this way, taking the partial derivative component wise would be little bit tedious, right? And the second method that just now we have learned, that this gradient is nothing but the A transpose plus A x, right? And if you look at this matrix is symmetric matrix, so that would be nothing but the 2A times x. So 2A is 4 2 to 6, and if you are trying to find the gradient at 1 2, so that would be 1 2, and that will be 4 plus 4, that is 8, 2 plus 12, that is 14, right? So both way you are getting the same answer, right? And it should be right. I think you have got the idea. So the idea was to just keep everything in a same framework, right? So that you can just apply the basics idea of the derivative to find the derivative of these kinds of functions as well. All right, now let's look at the function where the input that this function takes is from some n-dimensional space. So the input is a vector, and this function maps this input to or produces this output that is also a vector, right? So this is a vector function and it takes the input as a vector, right? So basically you can think of one example like the input space is in the two-dimensional space, and this function maps, this function f maps this two-dimensional space, and it produces the output that is in also in two-dimensional space, right? So vector input and the vector output, right? And we have already seen this kind of function. One of the example of this kind of function would be fx is equals to ax, right? Let's suppose this A is a constant matrix. That means if you change the x, if you change the vector x, there would be no effect on A. So let's suppose A is some 2 by 2 matrix, that is constant matrix, and this x is let's suppose it is from some two-dimensional space. So x belongs to some two-dimensional space, and let's suppose it has the component x1 and x2, right? And this f in this case will also belongs to some two-dimensional space, and it will have the component f1 and f2, right? So let me take a specific example so that you have the good idea that what kind of function we are talking about. So let's suppose if you have this A matrix that is 2 minus 1 and 1 3, and we have the x that is have the component x1 and x2, then if this function is fx is equals to A times x, then what will be this function? That is 2 minus 1 1 3 times x1 x2, and if you do the multiplication, what you will get is 2x1 plus x2 minus x1 plus 3x2, and this you can think of as f1x, f2x. So the function, this is fx, right? So the point is here, the input is a vector and the output is also a vector, right? Now what happens to the function if we change a little bit input? So let's suppose we are changing a bit this input, and we are trying to look at what will be the change in output. Right, so this is what the change in the output will be, right? And we have seen that is nothing but is equals to some linear operator times the change in input, right? And here this x dx is a little change in input, and this dx is also a vector, right? And this output, that is f, is also a vector, right? And if this input vector belongs to some n-dimensional space, so it has the size that is n, right? And this output belongs to some m-dimensional space, that means this has the size m. Then what will be the size of this linear operator? So it has to be, so अगर इन दोनों को मल्टीप्लाई करना है, इस वेक्टर को और इसको मल्टीप्लाई करना है, तो दिस हैज़ टू बी अ साइन, और अल्टीमेटली आपको जो है m कंपोनेंट वेक्टर प्रोड्यूस होना चाहिए. दैट मीन्स इसका जो साइज होगा, that is the size of this linear operator would be m cross n, right? Then if you do the multiplication, then you will get a, after doing this matrix times this vector multiplication, you will get a vector that will have the m component, right? So this has to be a size of m cross n, and it has the special name that we call, so this matrix has a special name that we call as the Jacobian matrix, right? If we have the function that is a single variable function, the linear operator turns out to be a slope, right, that acts on the change in input and gives you the change in output. If we have the function that takes the input as a vector and produces a scalar quantity, then in that case the linear operator is a gradient that acts on the change in input and produces the change in output. If the function that takes the input as a vector and produces a output as a vector, then in that case the linear operator is your Jacobian matrix, and it acts on the change in input and produces the change in output, right? And you must be familiar with from your multivariable class that how to find the Jacobians by taking the partial derivative component wise, right? We will just do the comparison, that how you used to do and now how we are doing, how we are trying to find the Jacobian, right? Now let me proceed and let me just take an example and show you that how you can find the Jacobian matrix or the derivative in this category of function. Right? Let's suppose, let me take the same example, that is fx is equals to ax, right? So this here x is some vector that belongs to some n-dimensional space, and this f also is a vector that belongs to some m-dimensional space, right? Because this matrix times this vector will give you a vector, and this A is a constant matrix that has the size m cross m, m cross n, right? So we are interested in finding what happens to the output if we change the input a bit, right? So just you need to put these things into the value. So that would be replace x with x plus dx, so that would be a x plus dx minus this term fx, that is ax. So here again you need to take care of the order, so that would be ax plus a dx minus ax, right? And this ax would get cancelled, so here the change in output, that is equals to this a times dx, right? And if you look at here, this is your Jacobian or f dash x, right? So in that case the linear operator is nothing but this matrix A itself, or the Jacobian, that is this matrix A itself, right? Now if you would have to do, or if you have to find the Jacobian, let's take this example where this matrix, this function is ax, and the function the a matrix A is this, and x, and let's try to find the Jacobian for this particular setting. So here, in order to find the Jacobian, what you will do, you will go component wise. So first what you will do, you will take the partial derivative of this f1 with respect to the variable x1, right? That would be 2, right? And now again you will take the partial derivative of this function f1 with respect to the another variable by fixing other variable fixed, and that would be 1. Then you will take the partial derivative of f2 with respect to the variable x1 by keeping other variable fixed, so that would be -1. And then you will take the partial derivative of f2 by keeping the with respect to the variable x2 by keeping the other variable fixed, and that would be 3. Now what you will do, you will put everything, all of these partial derivatives into the matrix form. So that would be del of f1, del of f1, del of f2, del of f2 with respect to x1, with respect to x2, with respect to x1, with respect to x2, right? And this is your Jacobian matrix. So that would be 2, 1, -1, 3, right? This is the one way of doing or finding the Jacobian. So you must have learned all these things in your multivariable calculus class. Now here we know what is the Jacobian, so we can directly make use of this. The Jacobian would be the matrix A itself. And what is this matrix A itself? That is 2, 1, -1, 3, right? So either you can go through finding the Jacobian component wise, or you can just do this way, and ultimately you will find that the Jacobian is nothing but this matrix A itself for this particular function, right? And again I am repeating the same thing. So I have derived this derivative from the scratch or from the basic definition of the differentiation, right? Here you can simply make use of the product rule. So how you used to do in the ordinary calculus, the same thing you can do, but again you need to be very careful about ordering, right? So if you you can just make use of the product rule here, or so the derivative of this would be derivative of a, and what you do, you keep the other as it is plus the a and then derivative of this variable x, right? And this matrix is a constant matrix, right? So that the derivative of this matrix A will be 0, right? 0 plus here A dx, right? And this is what you have found, right? And let me ask you one question: what kind of this 0 is? So this is not what will be the shape of this 0? So it will have the shape m cross n. So this is a 0 matrix, not only a scalar 0. So this is a 0 matrix, right? Alright, so now let's proceed further. Okay. Now let's assume that you have a function of this kind. Let's assume that fx is equals to g of hx, और यहाँ पे ये जो x है that is input, and this x belongs to some, let's suppose n dimensional space, right? So this h takes the input x as from some n dimensional space, and this h produces a vector that maybe is in the p dimensional space, and this g takes the input h that is from the p dimensional space, and let's say it produces some vector that is in the m dimensional space, right? So basically here you have the input x that is in the n dimensional space. Function h maps this input to some p dimensional space, and this goes to the g, that means this function g maps this input to some m dimensional space, right? And we are interested in finding the derivative of this kind of function. So basically we just need to here apply the chain rule, but here we need to be careful about the order, right? If I give you an example of ordinary calculus, you must have seen this kind of function, that is fx is equals to sine x square, right? And how you used to do the derivative? You are going to do first sine, the derivative of sine is cos x square, and then the derivative of x square is 2x, right? Either you can do this way, or you can do the derivative of x square first, that is 2x, then the derivative of sine x, that is cos x square, right? Both way is fine, but the natural way that you used to do is the first do the derivative of this sine, then go inside and do the derivative of this x square, that is 2x. Here everything is scalar, so this doesn't matter, the order doesn't matter. But जैसे ही ये वेक्टर और मैट्रिसेस के टर्म्स में हम लोग इनपुट आउटपुट के बारे में बात करने लगेंगे ना, तो ये ऑर्डर जो है पहला किसका डेरिवेटिव करना है और फिर बाद में किसका, ये मल्टीप्लिकेशन का ऑर्डर मैटर करेगा, राइट? सो यू कैन नॉट राइट दैट a टाइम्स मैट्रिक्स A इज इक्वल टू B टाइम्स A, right? This is not generally true. So that is what you need to take care of, and everything would be followed how you used to do in the ordinary calculus, right? So you can apply the chain rule, but you need to be careful. But let me give you an insight by going through the basics. So we are looking at the change in overall function, right? So this change is nothing but a function calculated at this change, that is x plus dx. तो हमने इनपुट को थोड़ा सा जो है चेंज किया, एंड बाय डूइंग दिस चेंज हम देख रहे हैं कि ये आउटपुट जो है कितना चेंज कर रहा है, राइट. एंड दिस इज नथिंग बट द लीनियर ऑपरेटर दैट इज एफ डैश एक्स टाइम्स डी एक्स, राइट. सो जस्ट लेट्स लुक पहले हम लोग सब बेसिक्स को देखते हैं कि चेंजेस कहाँ पे आ रहा है, कहाँ पे हमें ध्यान देने की ज़रूरत है. देन you can just directly apply the chain rule and you can have the derivative of this kind of function, right. So this change in output is equals to, so g h, आप x को क्या कर रहे हो, थोड़ा सा चेंज कर रहे हो, थोड़ा सा, right. So the function calculated at this point minus the function value at this, right. So this difference will give you the overall change in the function, right. And if you look at this term, that is this, ये क्या है, h x plus, let me write dx, not the delta x but the dx, right. That will be change in this h, right. If we have to write the change in h, this is how we can write, right. And this is equal to the, and इस केस में क्या है कि जो फंक्शन h है वो वेक्टर इन ले रहा है और वेक्टर आउट कर रहा है. So this will be f dash x times this change in input, and यहाँ पे जो f dash x होगा वो क्या होगा, एक जेकोबियन होगा ऑफ दिस फंक्शन h, जेकोबियन मैट्रिक्स होगा ऑफ दिस फंक्शन h, राइट. बिकॉज दिस h इज टेकिंग द इनपुट एज अ वेक्टर एंड प्रोड्यूसिंग द आउटपुट एज अ वेक्टर, राइट. और जैसे हम लोग लास्ट एग्जाम्पल में ही देखा कि दिस डेरिवेटिव इज नथिंग बट द जेकोबियन मैट्रिक्स. इसका साइज क्या होगा अभी हम लोग बात करेंगे. हियर दिस विल बी x एज वेल, राइट. नाउ we can look at this change in overall function, that is df is equals to g. You can simply put this, that is as hx plus dh minus g of hx, right. अगर आप इसको आप combinedly देखो तो आप क्या कर रहे हो, यहाँ पे h को थोड़ा सा चेंज किए, एंड चेंज करने के बाद हम लोग g को देख रहे हैं एट दिस पॉइंट, राइट, और g को देख रहे हैं एट दिस पॉइंट, राइट. सो दिस इज व्हाट, दिस इज नथिंग बट द चेंज इन फंक्शन g, राइट. और g क्या कर रहा है, इनपुट ले रहा है वेक्टर एंड प्रोड्यूसेस दिस वेक्टर. सो दिस चेंज इन g कैन बी रिटन एज द डेरिवेटिव, दैट इज द जेकोबियन of this function g of hx times change in h, that is dh. और यहाँ से आपने dh क्या है निकाला है, that is nothing. So we can write the Jacobian of this function g hx times dh can be written as Jacobian matrix of this function h, x and dx, right. So overall conclusion क्या है कि कंपोजिट फंक्शन है अगर जैसे g ऑफ एच एक्स है तो जो डेरिवेटिव होगा, सो दिस f डैश x इज नथिंग बट द प्रोडक्ट ऑफ द जेकोबियन ऑफ दिस फंक्शंस ऑफ g एंड h, राइट. और यहाँ पे सबसे इम्पॉर्टेंट क्या बात है कि ये क्या है, ये क्या मैट्रिक्स है, ये भी मैट्रिक्स है, इसका साइज क्या हो जाएगा. सबसे पहले इसके साइज में आते हैं, इसका साइज देखते हैं क्या होगा. देखो ये क्या है, नथिंग. इसमें अगर हम देखें यहाँ पे ये जो x वेक्टर है दैट इज फ्रॉम n डायमेंशनल स्पेस. सो दिस dx इज अ लिटिल चेन दैट विल बी हैव आल्सो द n दैट विल आल्सो बिलोंग्स टू सम n डायमेंशनल स्पेस. और जो आपका चेंज है दैट इज dh, दिस चेंज is nothing but the output that is in the p dimensional space, right. So इस जेकोबियन का साइज क्या होना पड़ेगा, इसका साइज जो है वो इधर तो n रहेगा और ये हो जाएगा आपका p. सो द साइज ऑफ दिस जैकोबियन h दैट वुड बी p क्रॉस n. सो इसका साइज हो गया p क्रॉस n, राइट. What will be the size of this Jacobian matrix? So the size of this Jacobian matrix, that will be ये देखो f जो है वो आपका किस डायमेंशन में है, m डायमेंशनल स्पेस में है, राइट. और ये जो h है वो आपका p डायमेंशनल स्पेस में है. दैट मीन्स इस जैकोबियन को क्या होना पड़ेगा, इधर तो p रहेगा और ये m, तो इसका साइज जो है वो m क्रॉस p हो जाएगा, राइट. अब देखो ये एक वैलिड मल्टीप्लिकेशन है, राइट. तो ये जो आपका ओवरऑल जो जैकोबियन मिलेगा उसका साइज क्या हो जाएगा, m क्रॉस n, राइट. अब यहाँ पे इंपॉर्टेंट बात क्या है कि आप इसका ऑर्डर को चेंज नहीं कर सकते हो. अगर आप इसके ऑर्डर को चेंज करोगे तो आपको मैट्रिक्स मिलेगा p क्रॉस n टाइम्स m क्रॉस p, राइट. तो देखो मल्टीप्लिकेशन भी वैलिड नहीं है यहाँ पे, मैट्रिक्स मल्टीप्लिकेशन भी वैलिड नहीं है, राइट. जैसे कि ऑर्डिनरी कैलकुलस में आपको फ़र्क नहीं पड़ रहा था कि हम साइन स्क्वायर को पहले करें, साइन का पहले डिफ्रेंशिएशन करें या एक्स स्क्वायर का पहले डिफ्रेंशिएशन करें, राइट. बट इन केस ऑफ व्हेन वी आर डीलिंग विद द इनपुट आउटपुट वेक्टर दैट इज मैट्रिक्स और द वेक्टर्स, देन ये जो ऑर्डर, जिस ऑर्डर में आप डिफ्रेंशिएट करोगे या वो ऑर्डर जो है अल्टीमेटली आपको मैटर करेगा, राइट. सो दिस कैन नॉट बी इक्वल टू, दिस इज नॉट इक्वल टू द JHX, that is Jacobian matrix times this the Jacobian matrix of HX, right, or is not equals to the derivative of this H or the times the derivative of G, राइट. अगर आपके पास ऐसे ही मान लो कि यह तो हमने दो कंपोजिट फंक्शन था यहाँ पे, अगर ऐसे ही रहता, अगर मान लो f ऑफ g ऑफ h ऑफ x, राइट. तो इस केस में आपको डेरिवेटिव क्या हो जाता है, f डैश g डैश h डैश, राइट. और फिर इसका ऑर्डर आप इधर उधर नहीं कर सकते हो, राइट. तो यहाँ पे ऑर्डर जो है वो मैटर करेगा. और यहाँ पे एक मैं पॉइंट और एम्फेसाइज करना चाह रहा हूँ कि एप्लीकेशन पॉइंट ऑफ व्यू से आप यहाँ पे जो डेरिवेटिव लोगे तो उसके बाद से डेरिवेटिव को अल्टीमेटली जब कैलकुलेट करोगे देन यहाँ पे एसोसिएटिविटी भी मैटर करेगा कि पहले आप इन दोनों को मल्टीप्लाई कर रहे हो या पहले आप इन दोनों को मल्टीप्लाई करके इससे मल्टीप्लाई कर रहे हो, राइट. तो वो फिर डिपेंड करेगा साइज पे कि इन दोनों को मल्टीप्लाई करना ज़्यादा इफिशियंट है पहले देन इसको, या इन दोनों को मल्टीप्लाई करके इससे मल्टीप्लाई करना ज़्यादा इफिशियंट है. वो कम्प्लीटली डिपेंड करेगा मैट्रिक्स का साइज क्या है, राइट. तो किस ऑर्डर में अल्टीमेटली आप एसोसिएट कर रहे हो आफ्टर कैलकुलेटिंग द डेरिवेटिव, एसोसिएटिविटी वहाँ पे थोड़ा मैटर कर जाएगा. और जो ऑर्डर है वो आपका वो तो थ्रू आउट द प्रोसेस मैटर करेगा ही, राइट. Alright, I think that is all, right. We will be looking at the Hessian in next lecture. Okay, so let me also mention that this, in case of a three composite function, here let me write also the order matters. सो इस केस में जो आपका डेरिवेटिव होगा दैट इज एफ डैश एक्स, दैट इज ए, फंक्शन ए का डेरिवेटिव दैट विल बी अ सम जैकोबियन मैट्रिक्स, फंक्शन बी का डेरिवेटिव दैट विल बी अगेन सम जैकोबियन, एंड फंक्शन सी का दैट विल बी अगेन सम जैकोबियन मैट्रिक्स. लेट्स अज्यूम करो कि ये जो एक्स है वो किसी n डायमेंशनल स्पेस से है. जब इस एक्स को आप सी में फीड करते हो तो आपको कोई वेक्टर मिलता है दैट इज p डायमेंशनल स्पेस, और जब इस सी के आउटपुट को b में फीड करते हो तो आपको एक वेक्टर मिलता है दैट इज़ इन q डायमेंशनल स्पेस, और जब इस b के आउटपुट को आप a में फीड करते हो तो यू गेट सम m डायमेंशनल स्पेस, राइट. सो द डेरिवेटिव ऑफ दिस वुड बी द प्रोडक्ट ऑफ दीज जैकोबियन मैट्रिक्स, और इनका जो साइज होगा दैट इज p क्रॉस n, q क्रॉस p एंड m क्रॉस q, राइट. तो अब जो है आप इसको जो फाइंड करोगे यहाँ पे, तो आप इन दोनों को पहले मल्टीप्लाई कर सकते हो, इन दो मैट्रिक्स को, फिर इसको c के साथ मल्टीप्लाई कर सकते हो, या नहीं तो आप किसी तरह से भी एसोसिएट कर सकते हो. इन दोनों को पहले एसोसिएट कर दो और फिर आप इससे a डैश से मल्टीप्लाई करो. सो ये यहाँ पे क्या इंपॉर्टेंट है ना, यहाँ पे इंपॉर्टेंट सबसे पहली बात है कि मैट्रिक्स का साइज क्या है, राइट. डिपेंडिंग अपॉन द साइज आप किस तरह से एसोसिएट कर रहे हो वो मैटर करता है, राइट. सो मैटर इन द सेंस कि वो कंप्यूटेशन पॉइंट ऑफ व्यू से मैटर करेगा. जैसे कि मान लो कि अगर आपने इन दोनों मैट्रिक्स को कैलकुलेट किया और ये एक वेक्टर है, राइट. सो दिस वेक्टर टाइम्स दिस मैट्रिक्स, राइट, विल हैव सम n स्क्वायर बिग ऑफ n स्क्वायर कंप्यूटेशन टाइम, और आपने इसको फर्स्ट मल्टीप्लाई किया एंड ड्यू टू मतलब जो भी साइज है, साइज के अनुसार ये एक मैट्रिक्स निकला, एंड दिस इज ऑल्सो अ मैट्रिक्स, राइट. सो multiplication of these two matrices would be of order that would be n cube, right. So the point is that depending upon the size of these three Jacobian matrix, associativity matters, right. end result सेम आएगा, बट अगेन कंप्यूटेशन जो है वो मैटर करेगा, right. So this is the just point that I wanted to mention, otherwise all okay, right. So what we have learned in this video, we have learned about the gradient and about the Jacobian. Next lecture we will just have a overview of the Hessian, and then we will be looking at the review on the probability theory. That is all in this video. Thank you so much.